Thank you. Great. Yeah, so thanks for holding out till the end of the day. I'd like to tell you a bit about Spark DataFrames and machine learning pipelines. A bit about myself. My name's Joseph. My background's in machine learning, and I work as an Apache Spark committer, primarily on MLlib, the machine learning library built on top of Spark, as a software engineer at Databricks. Databricks is the company which was founded by the creators of Spark and is driving its development. And our product, which I should have come more prepared with a good sales pitch for, is basically a great place to run Spark in the cloud. And you'll at least see a little bit about it when I'm doing some demos of these Spark aspects. And of course, guess what? We're hiring. Check us out. So about Spark. Thankfully, some people have talked about it already, and hopefully you've heard about it. If not, I'll just give a 1-minute summary. It's a distributed computing engine, basically emphasizing speed, ease of use, but being able to do sophisticated analytics. And it's an Apache open source project. I think one of the best things about it is in addition to the core distributed computing engine, comes with libraries for SQL or databases, streaming, machine learning, graph processing, all using APIs built to be similar to each other and very interoperable. They're very concise APIs in multiple languages, Python, Java, Scala, and actually an R API is going to be added in the next release. There, in addition to enterprises doing prototyping or development in Spark, there are some 500 plus enterprises using or planning to use it in production. And I think maybe an even stronger vote of confidence is looking at GitHub contributors over the past 5 years. You know, it started out as a project with 1 or 2 people working on it. Now there are some 100 plus individuals contributing every month. So, you know, in addition to the very early adopters, I think the next group of people were what you might call data engineers. People used to working with Hadoop, MapReduce, using functional programming APIs. Now, though, I think we're moving beyond that to be more accessible to data scientists and statisticians, people coming from R, you know, PyData, scikit-learn, those types of tools. And I want to talk about 2 elements of that today. First, I'll talk about DataFrames, which allow for intuitive manipulation of distributed structured data. And then also about machine learning pipelines, which allow for simple construction and tuning of ML workflows. So first about DataFrames. If you look at Google Trends for DataFrames, you'll see why it's a big deal. In recent years, usage has simply shot up. And here's why. It's a very simple concept. You know, it's a natural representation for data. You could imagine it as a tabular structure where you have basically data grouped into named columns. Here, a department column of type string, bio, CS, chem, an age column of type integer, and so on. But in addition to being like a natural representation, DataFrames come with a very friendly API. So if you've used Hadoop, then you know that going to Spark is a huge improvement in terms of reducing the number of lines of code which you've used. And this is the kind of traditional Spark RDD, or Resilient Distributed Dataset API, you might use to do a query on this table. It does something with the department column, something with age, but you probably can't figure out in this amount of time what it does, or actually that there's a little bug in it. But if you rewrite it using a DataFrames API, then you can immediately tell what's going on. You take your data, you group it by department, and then within each department, you're finding the average age. So this is what DataFrames, and in particular Spark DataFrames, are offering. This DSL for common tasks it has a lot of different operations: projection, filtering, aggregation, joining. It also allows support for metadata for columns, and also user-defined functions to do more customized queries. So our API was inspired by R and Python Pandas, so it's familiar to other users. But it has APIs in, of course, Python, Java, and Scala, and R in development. There's easy Pandas integration. You can convert to and from Pandas data frames with a single call. The difference, of course, is that these are distributed. So you can run this code on your laptop and then run the same code on a big compute cluster. The other part is that this code is highly optimized. And here, let me just show you an example, which was just run on a laptop, but gives you a comparison with how Spark was before. So this is looking at the runtime of aggregating some 10 million tuples of integers. And basically, to the left is better. The bottom two lines are showing the traditional RDD API in Python and Scala. The top two are showing it in DataFrames. And there are two things to note here. One is that with DataFrames, there's no longer a difference in runtimes between languages because of a unified implementation. The other thing to note is that, of course, the DataFrames run a lot faster. And that's because even with this very simple query, we're able to take advantage of Spark SQL's Catalyst optimizer to do a bit of query optimization and run faster. And of course, with bigger data sets, distributed data, more complex queries, it can make a really huge difference. So I'd like to just quickly demo the API. And I had hoped to do this using a live demo. But unfortunately, I don't want to rely too much on the internet holding out. So I'm just going to show something which I've already run. And this was just run on a single node. So this is in Databricks Cloud, but the actual calls can all be done in a Spark shell. And the only difference is some of the visualizations are only available in Databricks Cloud. So it's just looking at the 20 news groups data set. And you can load it, say, as a data frame from Parquet. If you're not familiar with Parquet, it's basically an efficient columnar storage format. Load some 11,000 documents. You can do things like display, and you see the schema, ID, topic, text for these documents. And then there are a lot of data frame queries that you can make. I won't, of course, have time to show them all. But for example, you can select the topic column, find the distinct elements, and collect them. And you see we get topics like science.medicine, electronics, and so on. You can group by count to find the articles per topic. And this is basically showing that there's a similar number of articles in each of these 20 topics. And you can do things like filter. Here it's looking for topics which look like science.medicine, and you can find the medical articles. So it's just a really simple example. But before I go on, I will show you this, which is creating labels we'll use in a later part of the demo. Here I'm creating a pre-processing call where I add a column to the data frame called label, which is created by taking the topic column, seeing if it looks like science, casting it to double. And so now we have 0, 1 labels indicating whether the article is about science or not. Here you can see we have some 2,300 science articles and 8,900 non-science articles. Okay. So good. That gives you just a taste of how the API is very familiar. And the main thing for you is that it allows development on a laptop, but can be highly optimized and run very quickly on a large computing cluster when you need to scale up. This allows computing, of course, with structured data, familiar APIs. But the best thing for me, from my perspective, is that it can be immediately used as a machine learning data set and plugged into ML pipelines. And I'd like to talk a bit about this now. If you're not familiar with Spark MLlib, it's one of the 4 libraries which ships with Spark. It started as a project out of Berkeley and entered Spark in version 0.8. And now a few releases later has had contributions from some 50+ organizations, over 100 individuals, and has a growing coverage of distributed algorithms. So these are all distributed algorithms. I'm not going to actually have time to go through them, but just to give you a sense, there's pretty wide coverage: classification, regression, clustering, recommendation, feature extraction and munging, stats, linear algebra, frequent item sets, and model import-export. But the motivation, of course, for talking about ML pipelines is that they're complex. Here's an example from Evan Sparks, a guy at Berkeley who's researching ML pipelines. And this is just an example of doing image classification. You don't have to see the individual parts, but basically there are a lot of them. And so if you actually develop this in practice, it's easy to come up with a wish list. First, you need to be able to specify that pipeline. Second, inspect and debug it. Third, rerun it on new data. And finally, tune parameters. Each of these elements may have parameters, and tuning them may improve performance, but doing that with a complex pipeline can, of course, be expensive and difficult. So for this, I'll use a running example using that data set we were just looking at with DataFrames, where our goal will be simply take the text document and predict whether it's about science or not science. And also, to explain the concepts behind ML pipelines, I'll use a very simple workflow where we'll load data, extract features, train a model, and evaluate it. So for loading data, we're able to take advantage of the data sources provided by DataFrames. Now, some of these are built in, Parquet, JSON, Hive, etc. But we also have an external data source API, and so we've built some on top of it, like Avro and CSV, and other people have added others. After we load our data, we'll have a data frame. And so I'm going to explain this workflow by showing the current schema of the data frame as it flows through each stage of this pipeline. We start off with a label column of type int and a text column of type string. Next, we'll extract features. And actually, for the demo, I'll be using two elements in feature extraction. The first will be a tokenizer, which takes the raw text and breaks it into individual words, adding another column called words of type sequence string. We then pass that to a hash term frequency module, which does the feature hashing trick talked about earlier today by Misha, taking those words and adding a new column, which is a fixed linked features vector. I'm highlighting these in blue because they take the transformer abstraction, which if you've used scikit-learn, you're probably familiar with. Next, for logistic regression, that's a model which can take any elements of this data frame it needs, in this case, label and features, train a model, and then output yet a new column of predictions. And then this is taking the abstraction of what we call an estimator, basically which takes a data frame and produces a model. And so, of course, finally at the end, then the evaluator can look at the prediction column, the label column, compare them, and see how well we did. So I'm explaining this where it's by default appending new columns, and that is the default, although you can change that. But there's some big wins from thinking about it this way. One is if you get to the end and you have terrible performance, you can go back and inspect intermediate results. And now that may sound inefficient because I'm keeping all these columns around, but because of the underlying optimizations of data frames, you don't actually have to physically keep that data around. You can materialize it whenever you need. And of course, in this example, it's tiny, it's not a big deal, but in a complex pipeline, being able to say, I need this intermediate result in my complex workflow, and having Spark SQL's optimizer automatically figure out the best way to compute that is really valuable. So here's our pipeline. And this is what an ML pipeline abstraction actually is. It's going to wrap the main elements in this workflow. It'll take loaded data, process it, and output something which can be evaluated. And the good thing about being able to wrap this as a single object is that you can get new data and rerun everything in exactly the same way, just this time with your trained model. The other good thing about this is for parameter tuning. So here, there is a simple pipeline, but say we have multiple parameters we may want to tune. Logistic regression takes a regularization parameter. We may want to sweep across a few values, find the one which works best for a particular problem. It gets more complicated, of course, when you also want to tune other things. For example, the hash term frequency module takes a number of features that you want to output, how long that feature vector is. And we don't know a priori if it should be 100 or 10,000. But what the pipeline lets us do is treat this as a single object so that we can do that parameter tuning jointly in an optimized way. we can pass that pipeline as an estimator in itself to a cross-validator module, which also takes the parameter grid we want to sweep over and an evaluator telling us, how good each model is. And it can automatically do k-fold cross-validation and find the best parameters. So I'll do a pretty quick demo of that, where again, I unfortunately won't rely on internet and will just scroll through something I've already run. Good, so here we have already created our data set, which has text and 0, 1 labels indicating science or not science. And we're going to be classifying these articles. So I import some stuff. And our goal is going to be to set up an ML pipeline with these 3 stages: tokenizer, hashing TF, and logistic regression. The tokenizer can be instantiated, and then you can set its various parameters. Here I'm just really setting the input column that it takes and the output column. Hashing TF, likewise, you can set things like number of features, and you can link it to the tokenizer by specifying its input column as the previous stage's output, and so on. So here I'm using fixed parameters. After I create these 3 elements of the pipeline, I can string them together, and now I have a pipeline with these 3 stages. Let me make sure people can see that. And finally, to fit it, I just do pipeline.fit, pass it the training data, and it does the sequence of feature extraction, model training for me. And of course, at the end, I want to evaluate the results. And you can see I can make predictions by transforming the training data set, selecting the columns I want. In this case, I'm selecting this new prediction column, which has the 0, 1 prediction. Now, after I do that, I can also use more principled evaluation metrics, such as area under the ROC curve. Basically, closer to 1 is good, lower is bad. Here I define a little function which transforms the data frame, selects the columns it needs, and evaluates it according to the area under the curve. And you can see on the training data set, we're doing awesome. We got 0.999, almost perfect. But of course, I accidentally revealed the text below, and the model is overfitted. If you load some held out text data, test data, and compute the ROC curve, then you'll find the area under the curve is 0.89, and so of course we're overfitting. Now the point of this is, of course, to motivate doing hyperparameter tuning. And so this is doing it using the cross-validator module, which will sort of automatically for us do k-fold cross-validation, searching over whatever grid we give it, optimized based on a metric. The particular parameter grid I'll show is just instantiated by saying, for number of features, sweep over these values, regularization, sweep over these, and then it instantiates all possibilities. Cross-validation is run basically by taking a cross-validator instance, setting the estimator to be the pipeline, how you want to evaluate it, the parameters, and number of folds, and then we can fit it. Now, after you fit it, you get this cross-validator module. You can select the best model from it and find it selected, based on this quick test, 10,000 features and regularization of 0.2. But you can see that that actually helped a bit in practice and brought the area under the curve for our test set up to 0.93 from 0.89. And so in practice, you may want to sweep over more parameters, do more than, I hope, 2 folds of cross-validation. But you can see that actually makes a big impact. And with a complex workflow, this can be really valuable, where you can wrap any element, however small, or the entire workflow in a cross-validation set. So after that, you can do stuff like use the Spark SQL API to save predictions to whatever formats, Parquet, text, etc. Good, so returning, basically I can sum up quickly. We had looked at DataFrames, which allow for computing with structured data using a familiar API based on R and Pandas, and which add on a distributed, optimized implementation. And like with all the other libraries in Spark, GraphX, streaming, etc., Those data frames are tightly integrated with a machine learning library, and we use them as our datasets and pipelines. We take a familiar API based on scikit-learn, but we add a number of things, including simple parameter tuning. There are also a lot of things which I unfortunately don't have time to mention here, but I'll at least list them quickly, list a few quickly. Schema validation is basically passing not the data itself, but the schema, description, or metadata about it through your pipeline to make sure that the pipeline will actually run before you invest the time and expense of running it for real. We have support for user-defined pipeline elements, both transformers, which can be used for things like feature transformations, etc., and also estimators, which can be used to learn whatever models you've created on your own. I also was showing very simple pipelines, just linear, but this actually has support for more complex ones. They can be composable, so you can have a pipeline within a cross-validator, which is sitting within a pipeline, and so on. And you can also have directed acyclic graphs, not just linear pipelines. So looking ahead, there are a number of things which are coming up, but I just tried to pick a couple bullet points. For DataFrames, we've been doing a lot of comparisons with industry benchmarks and look quite good, but we're still doing further optimizations and also adding an API in R. ML pipelines, we're especially working on better algorithm coverage and also pluggability, making it simpler for users to plug in their simple transformations or complex models very easily and pair them with things built into MLlib. We're also working on API for R in that case. Now, a lot of this pipelines work has been done in collaboration with UC Berkeley, where Spark came out of, and other organizations. I think one of maybe the most exciting things for me from it is work on auto-tuning models, which does something better and smarter than simple k-fold cross-validation, but can still have some guarantees. So that's a bit farther in the future, but I think is something interesting on the horizon. So looking at just a few points I want to give you for learning a bit more about this stuff, and I'm told the slides will be available on SlideShare, and so you'll be able to check out these links there. Learn about Spark, I'd start with the Spark Apache documentation. For learning about pipelines and data frames, we have 2 blog posts basically highlighting and giving pointers to more details. If you're interested in the Databricks cloud platform, which you saw in a static context without internet, basically it's a great place for running Spark, both handling low-level things like cluster management, jobs, etc., and also higher-level things like a nice GUI visualizations, collaboration, etc. You can see a demo and learn a lot more there. I think if you're interested in Spark, and especially ML on Spark, 2 MOOCs being offered alongside Berkeley on edX are coming up. Intro to Spark and also Machine Learning with Spark. And then finally, especially if you are working on Spark yourself or are just a user, then we have a Spark Packages Index, which is a community-driven index for any kind of packages built on top of Spark. So with that, I hope you'll check some of these out later, and I'd like to thank you very much.
Thank you very much. So, first, MLconf in Seattle is over. Courtney, you want to say a few things?